Thank you so much for the invitation. I want to acknowledge my collaborators at the bottom there. It's an incomplete list, and I'll mention more throughout the talk. So my work is focused on mainly optical surveys, using optical surveys to study AGN variability. And by the way, I'm told this is a broad audience, so feel free to interrupt. To be honest, I'm not used to giving talks to people outside of astronomy, so please feel free to ask questions. Yeah, what you'll notice here, so this is a typical light curve, high quality light curve of an AGN, which I'll talk about a little bit later in my talk. And what you'll notice is that the light curve is stochastic. So there's a stochastic variability, it kind of looks like a stock market graph or something like that. And in fact, we use some of the same modeling tools that people on Wall Street use.
Is it stochastic? It's not, there's no periodicity there if you graph it?
There's claims of periodicity, but it's not statistically significant in most cases. Yeah, there could be, and there are some unusual AGNs that do have some possible periodicity in the light curves. Those are candidates for two accretion disks, perhaps, or something else going on. So it's possible, but it's not usually seen. Good question. Yeah, so there, even though it's stochastic, we can still do this modeling and extract what could be fundamental properties, at least statistical properties of this light curve in a statistical way. And so one, that would be a time scale and then an amplitude. So that would give you sort of the two, in the simplest model, those two properties can describe pretty well the stochastic variability in AGNs that we see. So my talk is divided into two parts, and I don't know how much of it I'll get through, and that's okay. In the first part, I want to go over AGN variability, give a little introduction, and then talk about what we can learn about black hole accretion from observations of light curves in the optical, mainly, and how we can use these data to actually identify and weigh intermediate mass black holes, or IMDHs, which are, depending on your definition, smaller than, let's say, a million solar masses. And then in the second part of my talk, it's motivated by constraining models of supermassive black hole seeding and growth. So Priya and I have been working on this, and how we can use optical variability as sort of a new approach to try to inform our understanding of black hole seeding and growth. One of my first projects as a graduate student at the University of Illinois was to use data from this satellite called TESS to look at nearby AGNs. So on the left is a TESS image, and on the right is a ground-based image, actually, of this beautiful spiral galaxy, my favorite galaxy, NGC 4395. And now NGC 4395 is interesting because it's one of the most well-studied small supermassive black holes out there, and it's nearby, so it's easy to study. And it's been known to be highly variable in the X-rays and even in the optical. But until now, the light curve hasn't really been well studied of AGNs with black hole masses in this sort of lower mass range. And so, why the TESS satellite? So TESS, by the way, stands for Transiting Exoplanet Survey Satellite. And we might think, well, that's a little weird. Why are you using an exoplanet satellite to look at a galaxy, an AGN? But the reason, the image looks pretty crappy compared to the, Mount Lemmon. But what's great about TESS is we get 30-minute cadence light curves, space-based as well. So the photometric precision is good, and the cadence is really good. But the downside is it's a small satellite, small telescope. So it needs to be a really bright AGN in order to, be able to detect the variability. But I suggest that we look at this source because it's known to be variable and is very bright because it happens to be nearby. And we were able to extract this beautiful light curve from the nucleus of this galaxy using TESS, which is what I had on my introduction slide. And so we've done this sort of statistical modeling, which I'll talk about now. This is a kind of a busy slide. So just focus on this sort of plot here. These are simulated light curves, okay, on the right here. So the top light curve is just pure white noise, and the bottom light curve is this sort of red noise process called a damped random walk, which is the simplest model of AGN variability that I mentioned earlier, where you just have these two parameters, a time scale and an amplitude. And so what does the power spectrum look like of this damped random walk thing? Well, it's kind of simple. You know, it's so the power spectrum, by the way, sort of tells you the amount or the amplitude of variability that you get at different time scales or frequencies in this case, as it's usually defined in the light curve. And so what we see is this red noise pattern here, where you know you have this nu to the -2 frequency to the -2 power here. And then what happens is on longer time scales or shorter frequencies, there's a turnover, which means the variability power sort of flattens or dampens on longer time scales. And so if you just think about this intuitively, it kind of makes sense. You have this sort of stochastic variability on some time scales, but the average luminosity of that AGN isn't really changing on the time scales that we typically observe in most cases. So it has a sort of mean luminosity and it's fluctuating about that. And there are lots of analogies involving alcohol, which I'll skip. So in order to measure this power spectrum, though, you need really high quality light curves, which is difficult. Yes.
Very basic.
Yeah.
So on the physics plot, you showed that the fluctuations were electrons per second. This is just a CCD output, right?
Exactly. Yes. So
one pixel output, or
it's this little bubble here.
Oh, the right.
Yeah. So there's not many pixels on the test. Yep. Yeah, it's a game you have to play choosing the aperture and with tests to get the high signal to noise. Yeah. Great. Good question. Yeah, so because you're right, this is not really a physical unit. We aren't saying much about the amplitude here, but what I care about is the time scale. That's where I think the information about the accretion processes happens. So we've extracted this time scale, and let me just say quickly, it's really challenging to measure these power spectra correctly using like a gappy time series that you see here. You get all kinds of artifacts in the power spectrum, and there's ways you can overcome it using different things like the Lone-Scargill PSD, or what we've done here is we've done that, and we've also done this time series modeling using Gaussian processes, which you'll have to trust me is consistent with what you see using a power spectrum analysis, but works a bit better when you have these sort of unevenly sampled light curves with gaps due to the spacecraft has to turn around to send the data back to Earth and stuff like that. So so then once we get the time scale from this light curve using this Gaussian process thing, it also allows us to get nice uncertainties, and it's all Bayesian and everything, which is nice. We can plot this time scale. So this is log of the damping time scale, the turnover time scale in the power spectrum. It's tau damping there in days versus log of the black hole mass in solar mass units. And this is the previous work, which was Kelly et al. 2009, which is using ground-based data of nearby AGNs. And we thought, well, that isn't that interesting. Our source falls almost exactly on the extrapolation of this sort of linear regression using just the data from the more massive, supermassive black holes.
Yeah. So this model, the damped random walk, has a nu to the -2 slope for the spectrum.
Right.
I presume you could generalize it by giving it an arbitrary slope and fit for the slope from the data. So am I to take it that 2 actually works and you don't need to go to a more generalized model?
Yes and no. So we did try more generalized models. And so that's what you see. Actually, it's kind of underneath the karma there. So yes, we've done that. And in most cases, it doesn't really change much. That doesn't mean there's not something there, but it just means that the usually the quality of data that we have doesn't really warrant a more complicated model. Yeah.
But let us say you actually showed that it's 2. Is that telling you something about the underlying physical process?
Probably. I don't know what it would tell us, but yeah, probably. Yeah. And there are people who are, I think that's a new avenue.
Right.
Yeah, it's interesting. Yeah, good point. Yeah. Okay, so so this was interesting, but there were some, what you'll notice is, that's only one data point there, so you can still, make an argument. Is there really this relationship between the black hole mass and the time scale in these AGN light curves? And there's a large uncertainty in this relation when you extrapolate it, because, the previous data only sampled this range of like 10 to the 8 to 10 to the 10 solar mass black holes. So we thought, well, let's try to fill in this relation using smaller, they tend to be closer, more the Seifert type AGNs across this mass range here a little bit better, and see if this relation actually holds. And that would be quite interesting, because it means if we have a light curve here and we're able to build this relation, can we use this as a new way to measure the masses of black holes using the light curves alone? And it would depend on, the scatter and the relation and all those things. But that's sort of one empirical motivation for why we wanted to do this. And so I'll just jump to the results. So this is work that I led last year, which was published in Science. And this is the same figure as before, damping time scale versus black hole mass. And in this case, we've redone the analysis using higher quality light curves and being careful about how we do the analysis, and using as well a broader dynamic range in black hole masses from 10 to the 4 to 10 to the 9 or so solar masses. So that's what you see here in the black data points there. So we've gone from nearby dwarf galaxies with AGNs to NGC 4395 to SDSS quasars over there. And in comparison, we've shown the known correlation from the X-ray light curves. Okay, so it's basically the same analysis using X-ray light curves, and we plotted their damping timescales. And what we found is that first of all, the variability timescales in the optical are much longer. So they fall above this plot, days to hundreds of days compared to the X-ray, which is like hours or so. And the slope of the relation is also different. So that surprised me. That was interesting. And so what we think is that
are some of them the same sources?
A couple of them are, but yes, most of them are not. So that's a good point. Yeah. Yes. Yes. And so what we found is that the X-ray light curves seem to be consistent with, if you plot this orbital time calculation at, the ISCO, innermost stable circular orbit radius, you do that calculation at different black hole masses. The X-ray data roughly matches what you would expect for, just light, the time scale of orbital light at the ISCO. And so that was known. But, the question is then, how can we interpret the optical variability? I mean, there were all these, not all these, but there were some sort of suggestions that, well, maybe the optical variability is just reprocessed X-ray variability. The X-ray variability drives the optical variability in the disk. And well, maybe, but, we think this sort of rules out at least simple models of X-ray reprocessing on the timescales that we're observing here, because at least I don't see how you can get such a different relation, a different slope, versus black hole mass, if that's just reprocessed X-ray emission. They seem to have a fundamentally different scaling with black hole masses, which means maybe that's a different physical process that we're seeing. Yeah.
It looks like in the optical there's a turnover in time.
Yeah,
yeah.
What do you think about that?
That's probably, I don't know, because it's hard to do these measurements, because it turns out, for those more massive quasars, you need really long light curves. So, when you inevitably have to do some cut on how long the light curve you need. And so that gives you kind of a artificial turnover there. Yeah, so that's probably just a selection effect, really. Yeah, but it would be interesting, with Rubin, observatory, we'll be able to extend the light curves and with these objects, they're all in like, not all of them, but a lot of them are in the Rubin deep drilling field. So we'll be able to extend those light curves to maybe 20, 30 years. I don't know who's first.
Sorry, yeah. Are these all roughly at the same Eddington ratio?
Great question. Yeah.
Is there any dependence?
Yeah, they are roughly at the same Eddington ratio. And there's some mild evidence that there's some dependency on the Eddington ratio. Yeah, but we weren't able to really see any strong effect.
Is that published?
Yes, it's in
That's
the
very interesting.
yes, it's published. It's known. You can see it in larger samples, you know, with like worse quality light curves. But since we just opted for a smaller sample with higher quality light curves, it's hard to tease out any correlation in our data. But it doesn't mean it's not there. It's just a second order effect, I think. Yeah.
So you want to tease out. The eye wants to see things here on those curves. You mark T-or, which are the ISCO.
Yeah.
Curves of the orbital, not the ISCO, the orbital.
Yeah.
Maybe those are the ISCO for that. Those. Yeah. Are those for different masses? Or,
the two here.
But are they retrograde or prograde?
Oh, I'm not sure.
Yeah.
Because there's a factor of 10 difference.
Right.
In the ISCO period in retrograde and prograde.
Right. No, I'm not sure, to be honest.
I was wondering if you could tease out.
Yeah,
Spin.
I mean, maybe, you know, I think the X-ray data, you know, they don't use these Gaussian process techniques. You know, they have more evenly sampled data. I think there's some technical reasons to think that this scatter might just be like, you know, scatter in the data, the quality of the data. And I'm not sure if that's, you know, something you're seeing physically yet. So it's hard for me to say. But maybe, yeah. Wish I had a better answer.
You add a decade of scatter around this, right? It's the proportionality of mass which is being driven there. What's interesting is the proportionality of mass is somehow lost between these two curves. So,
right. Yeah, thank you.
Yeah. Factor in spin that's different.
Yeah. Okay, great. Anything else? Okay. Okay, so now, you know, we thought, well, okay, so we've done this for quasars and, you know, across dwarf galaxies, across a big range of black hole mass. So, you know, this might be a little controversial, but we thought, well, why stop there? You know, what happens when you look at stellar mass accretion disks? And so we plotted the stellar mass accretion disks here in magenta. So these are nova-like white dwarfs. From Scaringi et al. 2015, one of our collaborators on this paper. And what we find is that when we plot those stellar mass accretion disks, you know, so these aren't black holes, but they're compact objects with sort of, you know, rapidly accreting accretion disks. And when we plot that on this here, we see that that's actually consistent with our relation within about 2 sigma. And if you extrapolate our relation, but change the slope a little bit to 1/2, our slope is slightly shallower. You fix the slope to 1/2 black hole mass power law 1/2, then that actually goes through the data quite well. And so that's interesting. So, you know, is the power law, you know, 1/2? And so, you know, the question here is that in between is, and that's sort of the title of my talk, is the IMVH regime. So this is what excites me. You know, can we sort of interpolate this relation, if it's true, to use this as a new tool to find intermediate mass black holes, which in this case would have variability timescales of hours to maybe a few days, depending exactly on, you know, the mass that you want to target. So that I think has cool implications for Rubin and other surveys, where we really need high cadence data to you know, see the variability, that stochastic variability. So, you know, that's kind of an interesting motivator. We weren't allowed to talk about any of that in the science paper, but that's why we have to talk, right? So, okay, so, but, you know, there's still more that can be done with this data. So, you know, if the slope is 1/2, you know, how can we interpret that? And so what we've done is okay, so now this is our interpretation. So we've made some assumptions. We're going to make some assumptions here. So that was all empirical. But now let's use this standard model of accretion disk. So this is, the optically thick, geometrically thin, Shakir-Sunyaev accretion disk. And so, this is the equation for just a Keplerian disk to get the radius. So we think that let me put it this way. So we think that the optical variability that we're seeing in the optical should come from the optically emitting radius in the accretion disk. Okay. And so that's what we're going to, so that's tau here. Okay. So we know tau, but what's the radius? So we know tau, we know the black hole mass. Okay. And we're going to assume some fiducial value of alpha, which is the viscosity in the accretion disk, which is the other term here that this characteristic radius depends on. And we're going to plot that instead of the damping time scale. We're going to plot the radius. Okay. And when we do that, what we found is that so that's what's shown in the black lines here. So we recalculated it. And there's an additional dependence here on the mass. So that's why the correlation looks a little bit better here than you did on the previous plot. Okay. But so that's what we're plotting here in black. Okay, so then we compared this to the microlensing results, which are in blue. So this is accretion disk radii measurements from microlensing when a star passes in front of the AGN, the accretion disk, and you do some modeling of the gravitational lensing, you can actually infer the radius of the accretion disk, the typical radius optically, emitting part of that disk. And so assuming that optical microlensing behavior sort of matches the optical variability behavior, the radius in the disk, we can sort of compare the two, okay? And so that's what we've done here. And what we found is that, our correlation matches the microlensing results in blue. But what's really cool is that our correlation can probe the entire range of supermassive black hole masses, whereas the microlensing results, are also only looking at the more, brighter quasars that should have more massive black holes. So that was quite interesting. And in addition, you can compute. So I talked about the orbital time scale. So if you compute the orbital time scale here, you get one answer. If you compute the dynamical time scale in a standard accretion disk, you get another answer. And here I'm plotting the thermal time scale with alpha of 0.01. Remember, I said we assumed a fiducial value of alpha, the viscosity. And our relation here, it's not really shown, is more consistent with the thermal time with a higher alpha value of like 5%. So if you were to plot that, it would go, pretty much be consistent with this orange line here. So we think this at least shows that the variability timescales that we're seeing could be consistent with the timescale of thermal fluctuations in the accretion disk. It doesn't say anything about what drives those thermal fluctuations. That could be many different things. We don't know. But the fact that we're seeing this sort of normalization using the microlensing data and slope that seems to be consistent with a thermal time, if you believe that, then perhaps this favors viscosity of 5% at the UV emitting radius in the disk. Okay. Yeah.
So I'm a little bit confused here. I remember the story was microlensing disk sizes are too big compared to the standard.
Correct. Yes.
Here you're saying it fits. So what's different here?
Yes. So it fits with the microlensing data, which are too big, radii too big. So I think it's consistent. If we're basically taking the microlensing results as being true, right? To make this plot, we're trusting them.
I thought what this is saying is that the variability that you are measuring is consistent with microlens.
Yes.
Basically,
yeah.
Therefore, you're saying if I use the Shakura-Sunyaev model and made this plot, it won't be this line, it will be some other line because it will not agree with the data.
Yes, correct. So we've put that fudge factor in here. Yeah, it just changed the normalization.
Yes,
so
yeah.
the scalings, and things are all the same, but there's that fudge factor in there, which yes.
I'm sorry, I've not confused myself. I thought these slopes that you have, the dynamical time, the orbital time, all have the same mass scaling.
Yep.
But you ended up with a different slope with respect to mass in the previous part, or was that the X-ray data?
Yeah, so here I'm not showing the X-ray data. You know, yeah, if you tried to do that, it would have something else. Yeah.
So, but I thought your data has the non-orbital mass scaling.
Right. Yes. Right.
Why is it now matching the
Yeah. So, you know, it's been a while since I've done this calculation, but when you plot it, when you do that on this plot, you know, and you use the radius, because you're plotting it versus radius, then they all look the same. They all have the same, you know, the radius versus black hole mass looks the same. And then the normalization would be different. There's basically an additional, you know, mass dependence in there when you do this, when you plot it here.
I see.
Yeah.
Oh, okay.
It is confusing.
It's good because your timescale here is the downfill timescale rather than the orbital timescale, so that adds an additional mass dependence, which basically takes out.
Yeah.
It's the order.
Yeah, that's confusing to me too, but I thought the initial like the first equation that
Yeah, so that makes sense. Anyway, sorry.
Yeah.
Let's chat after.
Yeah, we'll chat after, and you know, I'll have to go back and read my paper. But yeah,
No worries.
and you know yeah, because the ISCO radius just scales with black hole mass. So anyway, so we think that's you know,
So I just
yeah.
one thing.
Yeah. Sorry.
I'm still hung up on this, and we'll talk afterwards.
Sure.
But the relationship between ISCO and mass of the black hole does depend on spin and whether it's retrograde or retrograde.
Yeah.
And while Daniel is right for spin, if you start at spin 0, I'm not sure where you're starting, then you get scatter on both sides. But prograde, if you're assuming prograde, it's only going to go one way when you go to retrograde. And that's going to shift that T orb. So,
Yeah, I mean, it's certainly possible that the, you know, things like the black hole spin could contribute to the scatter in both of these relations.
Yeah, but I'm talking about prograde versus retrograde.
Okay.
In which we go one direction.
Okay. Yeah, let's talk after. Yeah, I'm not sure. Okay. Okay, great. So with that said, I don't know, how's my time? Oh, perfect. Like halfway through. So okay, so now I'm going to change topics a little bit and talk about you know, the other half of my work here in my PhD, which is sort of this idea of, you know, constraining models of supermassive black hole seeding and growth. So this is an excellent figure from Mar-Meskua from her 2017 paper. And what this is showing here is redshift versus black hole mass. And so this, you know, represents three, well, let's just simplify it. So there's basically two different channels here of how you can form a black hole at high redshifts. And the idea is, you know, there's several observations of supermassive black holes at high redshift quasars. And, you know, how do you grow a black hole that's like 10 to the 9 or more solar masses at like redshift 7 or 8 so quickly? It's really hard to do with just standard, you know, Bondi accretion. And so the idea is that the consensus in the field is that you needed to have some sort of seed black hole there that formed with another mechanism that could then grow and accrete and have mergers that could form the supermassive black hole population that we see today. And so there's two different sort of camps for what black hole seeds could be, how they could form. There's the lighter version and then the heavy version, so light seeds and heavy seeds. And the light seeds, you know, in one popular theory are remnants of the first stars. So there's population 3 stars, you know, low metallicity stars, massive stars. There's theory out there that says that those the remnants of those stars could leave over black holes with, you know, masses 100 to 10 to the 3 solar masses or so. And then there's the other idea, the heavy seeds, which you know, one example could be direct collapse of primordial gas clouds under specific conditions. Those gas clouds could collapse directly into a black hole. In that case, they're predicted to be a bit more massive, like 10 to the 5 or so solar masses. but we don't know, and there's other ways, they can form. There's nuclear star cluster evolution and lots of complexities here. So this this is I just stole these from my paper, all these references here. There's a lot of work that's been done on this stuff in the theory out there. It's a really important problem in astrophysics and cosmology. But for an observer like me, how can we sort of distinguish, at least roughly, these heavy and light scenarios is what I'm interested in. And, if we can do that, then can we put some constraints on these models for black hole seeding and growth over cosmic time? And so what's interesting here is that for an observer, the fraction of dwarf galaxies, so low stellar mass galaxies, which host an AGN, which tend to have should have smaller black hole masses. So the AGN fraction there, or the black hole fraction, I should say, of those dwarf galaxies should trace the initial seeding mechanisms, okay? Between the light and the heavy seed, they get different predictions. And so there's this sort of leftover or relic IMBH population that we might expect to find. And depending on this fraction of black holes that these dwarf galaxies have, we can actually potentially just figure out which seeding mechanism is more likely to have the light scenario. So let's this is another way of looking at it. This is a great recent paper, Hadir from this year. And this is showing with the solid lines here, colored lines, different values for the occupation fraction. So again, the fraction of galaxies at a given stellar mass. This is stellar mass here, not black hole mass now. So the fraction of galaxies at a given stellar mass which host a black hole. So in this case, a central massive black hole that they can see in these simulations. And so what you see is that while they all sort of agree that with the observations that we think that pretty much every massive galaxy has a supermassive black hole in its center, whether or not it's active or not, it's a different thing. But we believe they all have black holes, supermassive black holes there. But for the dwarf galaxies, like 10 to the 10 solar masses or smaller, you get wildly different results because there's different prescriptions for the seeding physics that they put in these simulations, and there's different modes for how the host galaxy feedback and the black hole growth occur on these simulations, and they're designed to sort of match the scaling relations that we observe between like black hole mass and stellar mass of the host galaxy for more massive galaxies with quasars and supermassive black holes. But in the dwarf galaxy regime, things are still open. And this here is various probes from using like the traditional optical emission line ratios to look for AGNs. You see the fraction of those decreases using, this is a great paper, Miller 2015, looking at X-rays for central supermassive black holes, and they did some really robust statistical analysis, and so they have those results there. And those observations are also inconsistent because it's not really an apples to apples comparison. There's different wavelengths, there's different assumptions that are built into these observations. So it's an interesting problem, and the question is, can we use optical variability as a probe to try to distinguish between these different possibilities? Yeah.
What's happening at high masses?
What do you mean?
That some of them are going down.
At high masses?
Yeah, at least.
Yeah.
Yeah.
No, I don't know. Yeah, I'm guessing that's because the uncertainty is just blowing up there, maybe, and so that's what you're seeing. But that would be my guess. Yeah, I don't know. Yeah. Cool. Okay, so that was, I think, a really cool paper. And then there's other, I'll just quickly fly through. There's some other cool evidence for intermediate mass black holes, observational evidence out there. And these sources, I think some of these are more controversial still, but there are these hyperluminous X-ray sources. So these are probably compact objects. They have, in this case, X-ray luminosity of 10 to the 39 ergs per second. So that's like hyperluminous X-ray source. And this source was identified by its X-ray luminosity being so large, its spectral properties, and its variability. So if you saw this source in the center of the galaxy, you might think that's an AGN, maybe with a really low Eddington, perhaps AGN. Might not think twice about it, but what's interesting is this is on the outskirts of the galaxy. So that's interesting. So I want to make note of that. And so this is one of the most popular intermediate mass black hole candidates out there in the literature. And so there's a lot of these HLX things out there, by the way. And most of them are probably super Eddington accreting neutron stars or something like that. And that's true. But this source has some interesting other properties from its SED and its variability that seems to be consistent with an IMDH. But I think maybe the jury's still out, but that's an interesting source. Okay. And then there's this other one here, which is also off nuclear, and that's a X-ray tidal disruption event from May 2020. And both of these are consistent, using different methods, with a black hole mass of 10 to the 4 solar masses. Okay, so that's sort of an IVH. And then there's this other one, which is the GW 190521, the LIGO-Virgo binary black hole merger, which had a remnant mass of 140 solar masses. So that's by the technical definition of an IMVH, it's bigger than 100. So that's an interesting candidate for an IMVH. Now some people say that this is really just two it's just two black holes merged together and formed an IMVH. So it's not really like a seed remnant probably that we're seeing, but that's also interesting to have to put it on there. And then there's this other motivator for our work, which is, so this is work led by Vivian Baldassare, who sort of pioneered this business of looking for optical variability, so looking for AGNs in dwarf galaxies. So she has done a lot of work using optical surveys like SDSS and PTF to do this analysis using catalogs which have measurements of the host galaxy stellar masses. And she sort of did this search and looked for significant variability. And when you do that, you're able to get a fraction of, versus stellar mass of the galaxy, what fraction of those actually are variable and have an AGN in them, at least that we can detect, right? And what you get is these quite, she found these quite convincing low stellar mass dwarf galaxies that have these quite convincing stochastic variability that we might expect for a smaller supermassive black hole or something. So these are also quite interesting, and you can see that what's interesting is that below 10 to the 10, maybe, and 10 to the 9, maybe even 10 to the 8, the fraction of these dwarf galaxies that have this variability is non-zero. So that's quite interesting. But the problem is you can't really say much about the black hole seeding with just this variable fraction, because it depends on what fraction of those black holes are active and actively accreting, and what fraction of those actively accreting ones can you actually detect. So in order to sort of back out the IMVH demographics, we would say, or the occupation fraction here, we need a forward model or some kind of model which has all of these different, the selection function in there, the variable fraction, in order to learn something about the physics here. Yeah.
Binance, statistically, we should get more binance in smaller galaxies.
Are you talking about
like a black hole binary?
Oh, like supermassive black hole binaries?
So it's kind of merger of two dwarf galaxies.
Right.
Expect to have a binary.
Right.
And so some of that variability could be coming from a binary.
Sure. Yeah, I suppose. I haven't thought about it in the context of these results, so I don't know. But yes, it's possible. And if you look at those light curves, you might see something different there that would indicate if it's a close binary. But yeah, I don't know.
If you did a follow-up.
Yes, definitely. Yep. Yes. So, okay. So this is sort of the model now. So in order to so what we want to do, our goal here is to reproduce these observed variable fractions of AGNs across the whole mass range there on the previous plot, using a model which incorporates the different seeding scenarios, heavy and light seeding scenarios, and the different accretion physics that we might see, the fraction of obscured AGNs and all those things. So, there's a long paper on the archive which you can read, but I'll just give you the short version here. So we start with the input black hole mass function, and there's different possibilities depending on the different seeding scenario that you choose, okay? So they're all, consistent with every massive galaxy having a supermassive black hole in it here. So they all look the same for supermassive black holes. That's constrained, by observations as well, which I'll talk about in a second. But for the IMDHs, the number densities or the occupation fractions are unknown. So what we've done is we've assumed two fiducial models motivated by this Ricarte and Natarajan semi-analytic model here from their 2018 paper. And in blue is the heavy seed, okay? So you have more, in blue is light seed. So you have, more lighter, smaller mass IMDHs. And in magenta is the heavy seeds, where this sort of falls off a little bit faster here in the number density, okay? And so that's the heavy and light seeds there. And then we wanted to incorporate, because remember I showed you there's a lot of wandering or off-nuclear sources, right? So, these are both off-nuclear. So that's not really a central supermassive black hole. So if we want to say something about, what's the number density of these off-nuclear IMDHs that could be wandering around in even more massive galaxies, that's our attempt to model that there in green, okay? And how we did that is, Priya suggested, well, look at the Cecilia 22 paper, okay? So this is the number densities inferred from the LIGO-Virgo merger rates, okay? And so they've modeled this, and it's consistent with the observations of LIGO-Virgo mergers that you see here. This does weird things, out here to extrapolate it to stellar mass black holes. But there are some constraints here in the IMDH regime. Okay, now this doesn't really consider like the heavy and light seeding channels that I showed before. So that's why it kind of falls off here quite quickly. So it's sort of a lower limit you can make of it, I think. And so what we've done is we've just fixed this power law to the stellar mass, number density of stellar mass black holes, and made that consistent with the number density of supermassive black holes that we see. So that's the model in green here. So we just assumed some smooth power law there. There's no strong physical reason why it has to be that way. It's just a simple assumption. And our goal is to figure out, can we distinguish between these three possibilities using optical variability? Okay. And so after that, you put in the Eddington ratio distribution function. So, the fraction of these galaxies that we would expect to be accreting. And that's constrained from observations here. And that allows you, and we also did some SED modeling using theoretical SED models of different black hole masses, which gives you different results. And that allows you to plot the luminosity function. So this is same thing, the heavy, the light, and the sort of wandering, more optimistic, wandering IMDH scenario. And so this is the luminosity function here, okay? And here's NGC 4395 for reference, the one where we had the test light curve. And what you can see is that for the more luminous AGNs, accreting black holes, this is bolometric luminosity, we've fixed that to match the luminosity function, the local luminosity function of AGNs from observations. So that matches what you see in the optical as well as the X-ray luminosity function. You have to assume some bolometric correction, of course. There. But below a certain luminosity, the AGN luminosity function is not well defined. So in order to figure out, well, is this sort of optimistic, wandering black hole mass function crazy or not? What's some sort of upper limit from the observations that we can use. And so to do that, I use the luminosity functions from ultraluminous X-ray sources, which are like the HLXs, but not quite as luminous. And as well, X-ray binaries and globular clusters from these two papers here. And so take this with a big grain of salt. I mean, these luminosity functions are measured for like a handful of nearby galaxies with really good data. And it probably depends on like the star formation properties of the galaxies and things like that. But when you fold in the expected mass function for galaxies at redshift 0, you can plot the luminosity function there, the local luminosity function there, with some big uncertainty that I'm not even showing you on this plot, probably a factor of 10 or so. And our green, simple green power law is actually consistent roughly with those luminosity functions. So that reassures that, I don't think we can strictly rule out that number density for IMPHs in the local universe. Yeah.
Can you just explain what exactly you mean by wonders?
Yeah, so just wondering means an off-nuclear IMPH. So, most supermassive black holes are in the nucleus of a galaxy, but, especially for dwarf galaxies, they have smaller gravitational potential wells. So you would expect to find IMPHs that might not be into the center, might not have fallen into the center of the galaxy yet. So those might not be, those would be sort of wondering about the galaxy. That's the phrase that the community has kind of settled on to use. Yeah, yeah. Okay. Yeah, and so, you might say, well, yeah. And, you might say, well, one reason we haven't found a lot of these IMPHs is because we've not been looking for them, they're not expected to be in the nucleus. So.
Yeah, they'll just naturally come up from hierarchical galaxy formation, from the tidal disruption of satellite galaxies.
Right. Okay, so we've done that. And then the other question is, how can you predict what the variability amplitude would be of these AGNs? And so I'll go through this quite quickly. So I think we figured out how the time scale scales with the mass from the first part of my talk, roughly, empirically at least. And so what would the variability amplitudes look like? And so what we've done here is we've plotted the variability amplitude. This is basically the RMS amplitude of variability and magnitudes versus the black hole mass. And these are the results from the SDSS quasars here. There is some dependence with the variability amplitude, actually quite a large dependence on the Eddington ratio. So we think that, depending on the accretion rate or the Eddington ratio of that black hole, that would change the variability amplitude that you see. And that's what we see with like SDSS and Pan-STARRS observations. Those come out well. You can see the trends there with the color bar. And so that's SDSS quasars. But Franklin, Franklin Wong, who's undergrad I was working with at Illinois, who's now a grad student at Texas A&M University, has been looking at ZTF light curves of known dwarf AGNs. So these are optically selected AGNs from Amy Ryan's work, looking at broad emission lines in the spectrum and emission line ratios that are consistent with AGNs in dwarf galaxies. And using the ZTF light curves, you can actually, we've done some modeling and extracted the variability amplitudes of those AGNs. And what we found is that when you extrapolate the published relations from the SDSS results in gray, for IMPHs, it doesn't really work. You get sort of a ridiculous answer, like, 10 magnitudes of variability or 1 magnitude of variability or more, which wouldn't be right. I mean, an IMPH would be too easy to detect in that case. And so the key here, we think, is you have to consider the fact that the variability is diluted from the star formation in these galaxies. So that's an important problem for spectral classification, also for variability. It's there as well in a different way. It comes up again. And so that's what we've modeled here. We've done some simple, from these black hole masses. You can assume something from the relation between the black hole mass and the host galaxy stellar mass, and then assume a mass to light ratio to get the luminosity that you would expect in the ZTF band. And so there's a big uncertainty, but we found that with that correction, it seems to go through the data points there. So that was reassuring. And on the bottom here, we've shown two simulated Mach light curves for a supermassive black hole there, 10 to the 6 solar masses, and a IMBH, 100 solar masses. And what you can see is that, of course, the time scale changes. You have a much smaller time scale of variability there. And also the variability amplitude is much smaller. You know, we're talking of, you know, a tenth of a magnitude or so, a few tenths of a magnitude maybe for IMBHs. So you really need a really sensitive survey here to tease these out. Whereas if you simulate this, you know, you would get, depending on the accretion rate and things, it's easier to detect the variability there. Okay, so the end result. So we've plotted now using our model, forward model, and we put in the, you know, the simulated Mach light curves, except we added the cadence that you would expect to match Vivian Baldassarre's results from the PTF survey. So we added the cadence, the photometric precision that you would expect to get, basically the selection function from that data there, and plotted our model results for the light and the heavy seed. So the light seed in blue and the heavy seed in magenta. And with the PTF data, and her results here are shown observational constraints in red, which is just the variable fraction, again, versus stellar mass. In this case, I plotted it on a log scale, so it looks a little bit different than one I showed a few slides ago. But at least on this log scale, you know, the rough fraction of variable things matches our model, which was reassuring. But unfortunately, with the PTF data, it's pretty hard to distinguish between, you know, these two, at least in the local universe, these two black hole mass functions that we showed before. That information is lost in the, you know, number statistics that you get here.
Is the lack of number statistics there an observational problem, or is it because you don't think they're there?
No, that's an observational problem, I think. It could be that they're not there, but, you know, I think the majority of galaxies are dwarf galaxies. So if we have a more sensitive survey with better catalogs, that should improve drastically. Yeah. And then this is the same thing here, but with magnitude. So just to double check that our results there are matching with the recovered variable fraction versus magnitude. And it's not bad, considering all the assumptions we made. Okay, so now the question is, what do we expect with the Rubin Observatory? So Rubin Observatory is this, hopefully next year, it'll start taking observations on sky in Chile. Should survey the night sky every few days. And, you know, it's a large telescope, and you can look up the expected cadence and photometric precision models for that telescope with Rubin Observatory Survey, LSST, it's called, survey name. And you can plot, make the same plot here as before. And what we see is that we can actually distinguish between the two heavy and light black hole mass functions that we assume using LSST. So that's, I think, optimistic and interesting motivation for redoing this analysis with Rubin Observatory here in a couple of years. Now, what we don't know is how that wandering black hole mass function would show up in a plot versus stellar mass. That's really a main uncertainty here. So, you know, we can use Rubin to potentially find variable off-nuclear wandering IMBHs, but it'll be, I think it's an unsolved problem what those will, how to tease those out from, you know, all these plots like this, more sophisticated analysis. Okay, so assuming we can measure the black hole masses for these things, which is hard to do, you can plot the recovered black hole mass function with Rubin here. And in this case, we can do it for the wandering black hole masses. So this is not stellar mass now, it's black hole mass. So, you know, if we can use the variability time scale, say, to get a rough black hole mass with these light curves, and if we have a large enough sample with Rubin, which Rubin should give us, then we can get the black hole masses from the light curves potentially, and start to distinguish these seeding scenarios here on this plot without having to go through the host galaxy properties of the stellar mass. So that's, I think, really exciting. You know, it depends on the scatter and the black hole mass variability relation and things, but I think it's a promising future avenue to explore, and we get vastly different predictions for the three seeding scenarios. You know, some are quite optimistic, which, you know, I hope for. So I think it's really interesting future work. Okay, so I'm running pretty much out of time, but I just want to quickly talk about some of our other work. So we've been using dark energy survey data. So another photometric survey, smaller than LSST. But we've been looking into deep fields, which were used to find supernovae mainly. So we have this great 3-day cadence, you know, with gaps, seasonal gaps in between them. And we find these, you know, dwarf galaxies because DES is more sensitive than PTF for SDSS. We're finding them at higher redshifts. And so, you know, we've done some careful modeling of the spectral energy distributions of these galaxies. And you have to be careful because there's AGNs in there and things get, SEDs get complicated. But you can infer the stellar mass from the SED fitting there. And we're finding some, and in this case, we have an SDSS spectrum, which the signal noise isn't great. But from the magnesium-2 line, you get a black hole mass of 10 to the 6 or so solar masses. So not really an IMBH, I would say, but we're finding lower mass supermassive black holes using variability selection alone at higher redshifts. And so that's what this plot shows here. So this is the previous work using PTF and SDSS data in blue. And also Charlotte Ward's paper doing similar work with ZTF, Wiki Transient Facility. And our results here are shown for dark energy survey, deep fields. So, you know, this is a different way to attack the problem, I think. We're not necessarily finding more things at lower redshift because it's a smaller, you know, degrees on the sky is smaller, sky area is much smaller. But we're able to go deeper in redshift. So we're finding kind of lowish mass things at higher redshifts than before. So I think these are interesting because at higher redshifts, those IMBHs might be more pristine. Those galaxies should have undergone maybe fewer mergers and things than the ones that we see in the local universe. So those could be interesting objects to study further and to do it with LSST deep drilling fields. Okay, so just quickly, in summary, you know, why study intermediate mass black holes? Well, it's a test. One possibility is it's a cool way to test our understanding of accretion physics, and in particular on human timescales. So, you know, an IVH is sort of like a time machine. The black hole masses are smaller. All of the timescales that you would expect for the accretion and other things should happen on shorter timescales. So that'll be really exciting, I think, with Rubin to be able to do this analysis that's traditionally been done with quasars on smaller mass black holes. And not only to identify them, but to study their accretion properties. And but the challenge here is we really need ideally short cadence light curves to study them well. So hours to days cadence light curves. And some, you don't need to do it for a long period of time, but perhaps some ancillary survey to shadow LSST or something would be really great for IMBH science. And then constraining the models for supermassive black hole seeding and growth. You know, can we extend our forward model to do better using Bayesian techniques with Rubin Observatory? And then the possibility of extending this work beyond the local universe using Rubin or deep drilling fields to find lower mass black holes at higher redshifts using variability. And then another thing I haven't talked about at all, but sort of fits in with this science picture, is tests of black hole host galaxy coevolution in the IMBH regime. That's a super exciting window into this black hole host galaxy coevolution or not problem. And IMBHs might give us a new window into that. So with LSST Rubin and also LISA, you know, which I haven't talked about either, are really set to open up, I think, a new window on the IMBH population. And I hope this work can help us do that. So that's all. Thanks for your attention.
Thank you, Colin.
Thank you.
Great talk. Yes, please.
So, very nice talk, Colin. Curious whether you have any other candidates other than that one case of the IMDH variability measurements?
You're talking about this one?
Yeah.
This is the only one we have like a good spectrum of, but I have proposals in the works to try to get follow-up spectroscopy of these. And yeah, some of them are more convincing than others, I will say, depending on what the SED looks like.
So how many candidates do you have?
Oh,
a handful or?
Yeah, I mean, these here, depending on what stellar mass cut you want to use, it's a handful. Yeah.
Are there enough galaxies with tests to find wandering black holes?
Wandering black holes. Yeah, maybe. The problem with tests is, yeah, the photometric precision is really good, but the pixel size is so big that you end up including a lot of starlight there. But yeah, if it's wandering and it's in a part of the galaxy with less starlight, maybe. But it's hard to do that. That's, I think, a big data mining problem. I think it's interesting, maybe. Yeah.
So in your summary slide, point 3, could you say more about how you can use IMDH to test models of pH post-galaxy coordination?
Right. Yeah, so I haven't done work on this really, so I'm not an expert, but I believe the different seeding scenarios, some of them do have different predictions for what you would see. So there's relations between the mass of the black hole and the stellar mass of the host galaxy, or the bulge mass of the host galaxy, or the luminosity of the bulge in that galaxy, and you can plot those correlations. And they're quite tight for quasars, but does that hold for IMDHs? I don't think we know, and that might be an interesting avenue to explore. Do they fall off of those relations when they're an IMDH, and then somehow some of them grow, the quasars grow and come to fall on those relations? Maybe.
Especially the evolution with the redshift is not known. We know all these correlations, redshift 0.
Right.
Any other questions for Colin? Okay.
Thank you.
If not, thank you.